Welcome back. So let's continue again with the definition of an isomorphism. Let V O plus V O dot V be a vector space and W its own O plus W its own O dot W be another vector space. So let there be two real vector spaces. A bijective function L from V to W is called an isomorphism. This comes from Greek language. So iso means same or actually equal. Morphism, if I'm not wrong, means shape or structure. Isomorphism of V onto W if L V1 O plus V V2. Notice this is very important. V1 V2 are vectors in V. So their vector addition is being used. On the other hand, LV1, LV2 are vectors in W. You see, L take vectors from V to W. So these two vectors are now being added using O plus W. L of V1 O plus V V2 is equal LV1 O plus W LV2. This happens for every pair V1 V2 from V. Likewise, scalar multiplication. LR O dot V of V equals R O dot W of L of V times L of V. So scalar multiplication. So you get equality here for all real numbers R and every vector V in V. So notice the first line here, we say L respects vector addition. The second statement, we say L respect scalar multiplication. So to be an isomorphism, you need three things. Your L must be bijective. Second, it must respect vector addition. Third, it must respect scalar multiplication. We say that the vector space V is isomorphic to vector space W if there exists an isomorphism L from V onto W. If you can find a bijective function from V to W such that that bijective function respects vector addition and it respects scalar multiplication, you say V is isomorphic to W. Theorem. If V is an n-dimensional real vector space, so you have an n-dimensional vector space, then V is isomorphic to Rn. What is R super n? The vector space of columns with n entries. Real vector space of columns with n entries. So this vector space has its own standard vector addition and standard scalar multiplication. So that's the vector space your V becomes isomorphic to. Well, let's start. Fix an ordered basis. You know V is n-dimensional, so it has a basis of with n vectors. So fix an order, that is your set S, which is an ordered basis. I'm using usual plus and dot to represent vector addition and multiplication of V. Take any vector V in V, construct its coordinate vector that we saw in the in our previous video, how to find coordinate vector. So start with a vector V, find its coordinate vector. What are these coordinates? Those are the coefficients when you write V as a linear combination of these vectors. Let L from V to Rn be defined by L of vector V is the coordinate vector A1 through AN. So notice A1 through AN is in Rn, whereas little v comes from V. V can be any vector space. So from little v you obtain a column which is your function L. Notice we have already seen in our previous video that coordinate vector of V equals coordinate vector of W implies V equals W. That means L is 1 to 1. Okay, that's the definition of 1 to 1. L of V equals L of W implies V equals W. So that's a 1 to 1 function. 1 to 1 has another name, injective. On the other hand, take any column from Rn, any column. Well, that column gets you a vector V using this linear combination. In other words, there is a vector V whose coordinate vector is precisely the column you brought up. That means L is an onto function. Onto, another name for onto is surjective. Since L is both injective and surjective, L is a bijective function. Now, suppose vector V and W are in vector space capital V. Assume this V is A1 through AN of this linear combination, and W is this linear combination. Okay, so what does that mean? The coordinate vector of V is given by A1 through AN, and the coordinate vector of W is given by B1 through Bn. Further, what is the addition of these two vectors? Well, it's this linear combination plus this linear combination. Well, we have commutativity, associativity, and everything. So get the V1 vector together. You see, V2 vector together, all the way to Vn vector together. Okay. Once you do that, you get the coordinate vector of V plus W is A1 plus B1, A2 plus B2, An plus Bn. So you see the coefficients form your coordinates of the sum vector. On the other hand, this column can be split as this column plus this column. In other words, the coordinate vector of V plus W is the coordinate vector of V plus coordinate vector of W. So notice this addition is the addition among columns, whereas this addition, it is the addition among the vectors in V. All right. So L respects vector addition. So it takes two vectors, adds them within V. What is the result equal? It's as though L getting each vector separately and then add in the column space. Now let's try scalar multiplication. R be any real number, V be any vector. Since V is any vector, you may write it as a linear combination of V1 through Vn for some scalars A1 through An. That means if I multiply by R, so this is multiplication, scalar multiplication within V, it is R times this vector. But you know in V, scalar multiplication distributes, so R goes to each piece. So what do you get? RA1 through RAN are the coordinates of the vector RV. Well, among columns, you can bring out the R. This is the scalar multiplication in the column space. So it's as good as saying R times the coordinate vector of V. So L of RV is RLV. That means L respects scalar multiplication. Previously here we saw L respects vector addition. Now we have seen L respects scalar multiplication. So L is bijective. It respects scalar vector addition and it respects scalar multiplication. So L is an isomorphism. Here is a concrete example. Let P2 be the vector space of polynomials of degree less than or equal to 2. Then you know that the set 1t squared is a basis. If I fix an order, it is an ordered basis. Using this ordered basis, we see that P2 is isomorphic to R3. Okay, so Here is an important theorem, reflexive. It's called a reflexive theorem. Why? The statement is every vector space V is isomorphic to itself. What do you need? A function from V to V which is bijective, which respects vector addition, which respects scalar multiplication. Consider the identity function from V to V. Well, identity function is bijective. It is both one-to-one and surjective. Moreover, what is identity vector function on any vector, sum or otherwise, is itself. I of V plus W is V plus W. On the other hand, V itself is I of V, W itself is I of W. So I of V plus W is IV plus IW. Similarly, take any scalar real number and any vector. Then I of RV is RV. That's the identity function. On the other hand, this V can be written as IV. So IRV is RIV. In other words, I respects scalar vector addition and scalar multiplication. It is bijective. So bijective respects vector addition, respects scalar multiplication. So I is an isomorphism from V onto V. Okay. Symmetry. This theorem is called symmetry. If vector space V is isomorphic to vector space W, then W is isomorphic to V. Suppose vector space V is isomorphic to vector space W. Well, let's continue in the next video because this is a subtle theorem. Let's continue in the next video.